When you multiply two large integers on a computer, the result requires more memory space than the original numbers. Keep multiplying, and eventually the hardware runs out of bits to store the result, causing an overflow error. Standard integer arithmetic always grows towards infinity, which creates a fundamental conflict with the physical reality of finite computer memory. Division presents another serious problem. Dividing two integers rarely results in a clean whole number. Instead, it produces fractions or unpredictable remainders. If a cryptographic algorithm relies on division to reverse its mathematical operations, these remainders make exact decryption impossible to guarantee. You cannot reliably recover the original plaintext. Modern encryption protocols, like the Advanced Encryption Standard, require a strictly closed mathematical universe to function correctly. We call this closed system a finite field. It is a defined set of numbers governed by rules that act as an absolute mathematical boundary. Inside this boundary, every operation always returns a value that already exists within the set. Every element also has a guaranteed inverse, meaning every operation can be mathematically reversed. To make encryption work, we have to stop using standard integer arithmetic and map the rules of Galois theory into the physical architecture of the hardware. Building this system starts with the basic definitions from abstract algebra, where numbers are classified into sets based on the operations they allow. This nested hierarchy illustrates how sets are organized. We move from general groups at the outer layer, adding stricter constraints. The innermost box represents finite fields. To reach this level, a set obeys the most rigorous axioms, requiring total closure under addition and multiplication. We create the first boundary using modular arithmetic. By dividing numbers and keeping only the remainder, we force values to loop back around, much like the hours on a clock face. This clock arithmetic only forms a true field if the modulo boundary is a prime number. Non-prime boundaries generate zero divisors, which destroys the multiplicative inverses we need for decryption. As Évariste Galois proved, finite fields exist for prime numbers, but also if the total elements equal a prime number raised to a power. The box in the lower right, labeled gf of p to the power of n, represents the specific mathematical structure serving as the backbone of digital cryptography. Because computers process data using electronic switches, the base prime number is always 2. This restricts our entire algebraic universe to coefficients of 0 and 1. By selecting a Galois field of 2 to the power of n, theoretical mathematics synchronizes with the binary states of transistors. Within a processor, any sequence of n bits can be expressed mathematically as a polynomial with a degree less than n. We represent a byte like 10110000 as x to the 7th plus x to the 5th plus x to the 4th. We translate this into hardware by stripping away the variables and keeping only the binary coefficients. This source demonstrates polynomial arithmetic inside a base 2 field. In panels A and B, working modulo 2 means 1 plus 1 equals 0, making addition and subtraction the exact same operation. The addition columns show a complete absence of carry operations. Because there are no carries to track, polynomial addition is exactly equivalent to a standard bitwise XOR instruction. This is highly efficient for hardware. An XOR instruction can execute across an entire processor register in a single clock cycle. In a GF2 to the n field, the CPU's physical logic gates perform the mathematical operations directly. Polynomial multiplication is more complex because it increases the degree of the resulting mathematical terms. Multiplying a polynomial by x increases every exponent by 1, which is executed in hardware as a simple logical left shift of the bit string. This shift pushes the leading bits outside our 8-bit field, which would normally result in a hardware overflow. We prevent this by implementing modulo reduction using an irreducible polynomial. An irreducible polynomial is the algebraic equivalent of a prime number. It has no divisors other than itself and 1. This calculation shows the specific polynomial multiplication and reduction arithmetic used in the Advanced Encryption Standard. The long division step at the bottom shows the overflowed polynomial of degree 13 being divided by the AES irreducible polynomial to return an 8-bit remainder. In a physical processor, this reduction is a conditional XOR triggered whenever a bit shifts past the highest register boundary. This shift and XOR mechanic ensures the memory footprint remains static while the data is transformed through the field. We can view the complete operational landscape of these rules in a 3-bit Galois field, GF2 to the 3. In this addition matrix, every possible combination of inputs results in a value that stays strictly between 0 and 7. The multiplication matrix for this same field follows the same rigorous logic. The internal grid shows no empty cells and no zero divisors. No values can escape the defined boundary of the field. To prove this system is suitable for cryptography, we must verify the existence of exact division. This table calculates the multiplicative inverse for every element in the field. The third column confirms that every non-zero element has exactly one mathematically precise inverse. This existence of a unique inverse guarantees that data transformed through these polynomials can be perfectly reversed. By using the strict rules of Galois fields to dictate transistor logic, we transform abstract algebra into the reversible, computationally secure operations that define modern encryption.